Okay, I think we're going to switch screens and get started. Now, obviously, it's just a blank screen for a lot of you at the moment. Um, but hello, everyone. Welcome back, my good old chemistry kings and queens. We're back for another exciting chemistry squad. And today we're going to be looking at exothermic and endothermic reactions. So it's going to be really, really exciting. I've just got the whiteboard up, so hopefully you can all see that. But just like normal, we're just going to start off with saying a few hellos, everyone get comfortable, um, and as much engagement in the chat as possible. It's always great to see so many of you turn up for another exciting, very short, very brief um, chemistry squad session. I can see a few people sort of popping in now, so yeah, we'll probably get started in the next 5 minutes or so. But how is everyone? It'd be great to see some hellos. I'm not too bad myself. It's really cold today, actually. When I left the house this morning for work, it was about 1 degree Celsius, which is honestly crazy to think about. Um, but hopefully, all of you are staying warm as well, wrapping up appropriately. It's around this time of year that people get ill. So, um, and you know what? I guess it's quite funny that I've said that because today's lesson, or half of it, is going to be about exothermic reactions, which I'm sure all of you know is related to an increase in temperature. So no pun intended there. But yes, we will be kicking off in the next 5 minutes or so. So if you haven't already, do get a drink, get comfortable, get your notes out if you'd like to. By all means, you're allowed to refer to your revision guides or your school notes as you're tuning in and as you're learning. So you're always more than welcome to. Let's see, a few more people have joined. Don't be afraid to say hi. Do pop a hello in the chat or an emoji. Absolutely anything. Be great to see some of you. We do have our lovely mod, Inga, who is moderating as always. Thank you for moderating. Inga has put a very useful link in the chat where if you click on that link, you can refer the squad to your friends and you can also get reminders so that you get reminded about my chemistry squad that happens every Wednesday for half an hour at 5 p.m. I'm also going to take this moment to also plug the other squads that happen in the week. So you have Sarah's that happens on a Monday, and that's all about maths. And you have Fliss's, which happens on a Tuesday, which is all about AI and IT. So really, really exciting, interesting content there. Definitely worth checking out. Definitely worth signing up for. So if you haven't already, do make sure to check out these other squads. But we will be getting started on the content itself in the next 3 minutes. But we're just going to have a little bit of time at the very beginning for everyone to get comfortable, for everyone to sort of join, and then we'll just get right started. We'll just get started in the next 2 to 3 minutes. But hopefully all of you are enjoying the chemistry squad. And again, I do need to say thank you to all of you who do join on a weekly basis. And the reason that I say thank you is that without you, there isn't really a chemistry squad. And that's the really important thing. There is no chemistry squad without all of you. And so I do want to say thank you for tuning in every Wednesday. And I do want to say thank you to all of you students who tune in to the My Tutor squads that happen weekly. It's a lot of work to put all these together and to coordinate it. So seeing all of you engage and seeing all of you get involved, it definitely makes a difference, and it's definitely the highlight of my week. So thank you. Swampert01, hey, how are you? I hope you're well. I hope you've had a good day. I hope it's been a productive day, and I hope you're excited for another session all about chemistry. Hey Latona, hi, good to see you this evening. Hope you're also well. Great to see some engagement in the chat. So great to see you. Thank you for joining. It does make a difference having every single one of you join and engage. So hello to you as well. Thank you for joining us this evening. Today we're going to be going over exothermic and endothermic reactions. So do make sure to get strapped in for some really, really exciting content. So great opportunity to revise a topic which I think can catch a few people out. So it's definitely worth going over. How's everyone's day been? It's been okay, hopefully productive, hopefully not too busy. Lila, hello, it's good to see you. Thank you for joining this evening. It's always great to have as much engagement as possible. So great to see you this evening. I think we're just going to get started, and then if anyone does want to say hi, how are you, etc. as time goes on, then as always, I'll always say hello. Always make time for you guys, because without you guys, there is no chemistry squad, and so I do want to say thank you to joining. But yes, let's just get right into it then. Let's get right into it. So, we are going to be looking at exothermic and endothermic reactions today. Okay. Now, before I get into it, who has some ideas on what exothermic and endothermic reactions are? What do we all think? What are some ideas that come to mind when I say endothermic and exothermic reactions? What do we all think? And then whatever we come up with, I'm going to type in the lesson space or on the whiteboard space. So what do we all think? What comes to mind when I say exothermic or endothermic reactions? It could be a word, it could be a phrase. Exo exo energy given off, endo energy goes in. Thank you, Charlie, for that contribution. Great to see you again, mate. Thanks for joining. And Annabelle gives off heat and absorbing heat. Fantastic. So well done, Charlie and Annabelle. Those are absolutely brilliant contributions, and I'd agree with that. So we can say that exothermic reactions are all to do with energy being released, or almost being given off in a sense. I'd agree with that. And we can also say that endothermic reactions are those where energy is being taken in. So I definitely agree with those. And I'm going to change this to blue. I always think of the color blue anytime I think of, endothermic reactions. I'm not too sure why, but yeah. So that's fantastic, guys. Well done. Actually, I'm going to move the text a bit because I think my face is covering it. There we go. Fantastic. So, exothermic reactions, energy being released, and endothermic reactions are energy being taken in. Now, anytime we think about any reaction, we can think about the entire setup in two compartments. We can think of it as the system, and we can think of it as the surroundings. So I'm going to attempt to draw a conical flask to show you what I mean. Now, when we think about the system really refers to the reactants. So if I have a reaction in which A plus B gives me C and D, okay, that is the system. Okay, so the system really refers to the reactants, okay, and the products. The surroundings is then everything else. So that involves the beaker, it involves the air around the beaker, it's essentially everything else that's not the reactants and not the products. And so, what we then have to try and think about is how energy is exchanged between the two. Okay, and let's write that out actually. So we are going to say that this area of chemistry looks at energy transfer between the system and the surroundings. Okay, so that's what we're really thinking about here. So your surroundings are everything around the reactants, and then the system is the reactants and the products themselves. Now, I want you to all remind me, and I'm gonna roll over in my chair to get the little trophy that's on my shelf, if you get this right. But I want all of you to remind me. Just type in all caps, whatever in the chat. Remind me, what is the law of conservation of energy? What does the law of conservation of energy state? What do you all know? I want to see loads and loads of responses here. I can see loads of people are viewing right now, so I want to see that number of responses in the chat right now. So, what does the law of conservation of energy state? Got one response from Charlie. Brilliant. All the responses are coming in now. Wonderful. Okay. Okay, this is fantastic, guys. Well done. Great. And so, as promised, I'm going to roll over. And there you go. You've earned this. You've earned this golden trophy. Well done for answering that. Spot on, all of you. So, the law of conservation of energy states very, very clearly that energy cannot be created or transformed. Energy cannot be created or destroyed, only transformed. So, in a reaction, you can't destroy energy and you can't create energy. In short, it all has to add up at the very end. So, whenever we look at an endothermic reaction or an exothermic reaction, we are really thinking about how that energy is transferred between the different interfaces. So we're looking at how energy is transferred from the system to the surroundings in the case of an exothermic reaction, and we are looking at how energy is taken into the system from the surroundings in an endothermic reaction. Does that make sense to everyone? Give me a quick thumbs up in the chat if it does make sense. Me, Sam, hi, thank you for joining this evening. Hopefully you caught that explanation about endothermic and exothermic reactions just there. Do give me a thumbs up in the chat if that made sense to you. See a thumbs up from Charlie, fantastic, smashing it. A Latona, I see a thumbs up from you, smashed it, well done. Am I going to see any more thumbs up? I know a lot of you contributed to that answer, so I want to see more thumbs up. If it doesn't make sense, let me know. Put a thumbs down, put a sad face, and tell me what doesn't make sense to you, and I will happily go through it again. We want to make sure that everyone understands it so that everyone is a chemistry king or a chemistry queen by the end of this session. Lila, fantastic. Okay, that makes sense. And Annabelle, I see a laughing smiley emoji. I'm assuming that makes sense and that you're finding it entertaining. It's two birds, one stone. Fantastic. So, that's brilliant. And Misan, that makes sense to you. Fantastic. So, we know what exothermic reactions are. We know what endothermic reactions are. That's fantastic. You're smashing it, guys. Well done. Now, the next thing to then think a little bit about is to think about how we then characterize endothermic reactions and how we characterize exothermic reactions. Now, I'm sure a lot of you already know the answer to this, and the way that we characterize and identify them is based on temperature changes, okay? What we know is that if a reaction is exothermic, we tend to see an increase in temperature. And similarly, if we have an endothermic reaction, we tend to see a decrease in temperature, okay? So that's what we tend to see, okay? An exothermic reaction, increase in temperature. An endothermic reaction, a decrease in temperature. And we're thinking about the temperature of the surroundings. And there are a good few examples of these that you may have even come across in everyday life. So a really classic one for an exothermic reaction is if you burn something. Now, I remember that I used to go camping with my dad a fair amount when I was younger. And there was one instance in which we lit a campfire, and it's just combustion, isn't it? So combustion is a really good example of an exothermic reaction because energy is being transferred to the surroundings from the system, okay? And so that's a good example of an exothermic reaction. An endothermic reaction, for those of you who may have played sports, you know those ice packs you can kind of break open or you kind of snap it and it goes cold? That's an example of an endothermic reaction because it gets colder, okay? Mikhail, hi, you just joined. Welcome. Great for joining us. You've not missed too much. So far, we have just gone over what exothermic and endothermic reactions are, and we're just talking about how we characterize them. So we're just talking about how exothermic reactions are related to an increase in temperature, whereas an endothermic reaction is characterized by a decrease in temperature. Okay, so here's a good question from Balloon Agent. So is photosynthesis an endothermic reaction or an exothermic reaction? I think that is a very good question. And in short, I think it depends on which stage you think about photosynthesis. Okay, now photosynthesis arguably is where we take energy from light and we store it in a high energy product, and we know that to be glucose. So we would then say that photosynthesis is entirely well done, Adeli, beat me to it. It's an endothermic process because we're taking light. Could I make my screen a bit smaller? Oh, yeah, I can make my webcam a bit smaller. Yeah, sure. Give me 1 second. There we go. There we go. Excellent. So yes, photosynthesis is an endothermic process because if we think about what photosynthesis is, we're taking light energy and we are converting that into glucose, aren't we? The energy from light, we're turning into glucose, we're storing that energy. So it's endothermic in process. Hopefully that makes sense. That answers your question. But yes, going back to what we were saying, we know that exothermic reactions are equated to an increase in temperature, endo a decrease in temperature. Now, one of the things that you will definitely need to know for your exam is know about your enthalpy level diagrams. And I'm sure all of you love these. I know I did. Hopefully you detect the sarcasm. But honestly, they're not too bad. It's just about knowing which one is which. Now, I'm going to attempt to draw one of these enthalpy level diagrams. And I want all of you to tell me whether it's endothermic or exothermic. As you can see, I'm not the best at drawing. So we're going to draw that. We're going to draw that. And we're going to do that over there. Okay. And we're going to have time over here. And we'll have enthalpy. We'll put nth for now because I haven't got my graphics tablet. So, looking at that diagram, is that an enthalpy level diagram for an exothermic reaction or an endothermic reaction? And for bonus points, I want you to tell me why you've answered that. These two answers, Misam, you've said Misam and balloon agent, you both said exothermic. Okay. Latona, you've also said exothermic. What else have we said? Let's try and get one more answer. Sorry, someone give me one more answer, and then we'll move on to the explanation. Just one more answer. Who's going to be the first one? Are we going to continue the trend of exothermic, or are we going to say endothermic? Exo, fantastic. Okay, so you are all correct. It is an exothermic process, and both Balloon and Charlie have given a really, really good explanation. Okay, what you can see here is that this graph shows your enthalpy. Okay, I could add to this diagram, and I could say that on over here, I've got the enthalpy of the reactants, and I'm going to move this over here, and I've got the enthalpy of the products. Okay. Now, we said earlier that energy can never be created or destroyed. It can only be transformed. So, because of that, we can say here that actually the reactants have more energy than the products. Now, if we're saying that energy cannot be created or destroyed, only transformed, that must mean that that excess energy has to go somewhere. Where does it go? It's being transferred to the surroundings, which we know is characteristic of an exothermic reaction. Because we know in exothermic reactions, energy is transferred from the system to the surroundings, and as a consequence, we then see an increase in the ambient temperature of the surroundings. Okay, does that make sense for everyone? Give me another thumbs up in the chat if it does make sense, or a smiley face, absolutely anything. Well, not absolutely anything, but yeah, give me some level of confirmation that what I've just said makes sense. So I've got a yes from me, Sam. Fantastic. Charlie said good. Evelyn, hi. Good to see you. Wonderful. Smiley face. That's great. Lila, great. That makes sense also. Fantastic. And a laughing emoji from Mikhail. Fantastic. It all makes sense. Everyone's happy. Now, I'm going to draw something on the board in a different colour, and I want you to tell me what it refers to in this graph. I'm going to do it in yellow. This yellow arrow I've just drawn, what does that refer to? What do we think? What does this refer to? I see activation energy. Oh, you guys are smashing it. Okay. It's the activation energy. Lyrics, hey, good to see you again. It's great to have you here this evening. It's the activation energy. Yeah, well done, guys. So Mikhail, Balloon, and me, Sam, well done. It's the activation energy. Now, what is the activation energy? It's going to be a bit of a tricky question. How would you all define the activation energy of a reaction? What do we all think? For the record, I'm not sponsored by Coca-Cola at all. I'm not. How much energy it takes to break bonds. Okay, that's what I've got from Balloon. What else do I have? Do I have something else? Me, Sam, the minimum energy needs to start up the reaction. Yeah, okay, fantastic. Let's get one more answer. The minimum quantity of energy which the reacting species must possess in order to undergo a specified reaction. Okay, fantastic. You guys are smashing it. Again, I'm going to hold up the little golden trophy for you. You guys are absolutely smashing it this evening. But yes, that is the activation energy. All of you are correct. Now, whenever we think about any reaction, what we need to remember is that we need to put energy into the reaction in the first place to get it going. Now, I'm going to give you an example. I've got this piece of paper here, right? Now, this piece of paper is basically carbon, isn't it? And if I were to write out a reaction where I burned carbon, all I need is oxygen, and that would produce carbon dioxide. We're all in agreement with that. There's oxygen in the air around me. I know that because I'm breathing. This is my carbon. But this is not turning to carbon dioxide right now. It's not on fire. I would need a match of some sort to get this to start burning, and a match is a source of energy. Okay? Any reaction requires an input of energy to kickstart the reaction, and generally that refers to breaking the bond in the first place and bringing the molecules up to an energy level where they're more likely to react. So if we look at this graph here, this initial incline is the activation energy. This is the energy required to get the molecules to a point where they are likely to react, after which they then go down the curve. But ultimately, what we need to remember is that the net energy change, or the net enthalpy change, is this arrow here. Okay, and we call this delta H, and it's delta H negative. Okay, because we see that enthalpy is being transferred from the system to the surroundings. Okay, and so a bit of a tip for you when it comes to your exams. Anytime you're asked to calculate an enthalpy change for an exothermic reaction, you must always remember that your answer is negative. You must remember to put and specify the sign, because if you don't, you could lose marks, because by putting a positive, that may imply that you think the reaction is endothermic, which we know it isn't. Does that make sense for everyone? Give me a quick thumbs up if it does make sense. So Misa, you've asked, is that the overall energy change? Yes. So the green arrow will be the overall enthalpy change. Fantastic. You're smashing it, guys. Well done. Well done. Really proud of all of you. You guys are doing brilliantly this evening, as always. Charlie, well done. Great. But this is why we are the best chemistry squad out there. Right? This is why I refer to you as my chemistry kings and queens, because you are absolute royalty when it comes to learning this. I think it's absolutely great what you guys are doing at the moment. So, we know that this one is an exothermic reaction. Let's do the same for an endothermic reaction. Yeah? So we are going to clear the whiteboard again, and we are going to do the same thing for an endothermic process. So, it's going to look like the opposite, isn't it? So the curve's going to go upwards, like so. And here we have our reactants. And I did say we're going to do this one in blue, since endothermic reactions are always related to the colour blue. And that didn't change for whatever reason. Let's have a look. There we go. So we've got reactants over there. And then we've got products over here. Okay. Fantastic. Okay, so this is what your enthalpy level diagram would look like for an endothermic reaction. Your reactants have less energy than the products, So energy is actively being taken from the surroundings and being put into the system to promote them to a higher energy level. Okay, so that is your exothermic and endothermic reactions, and that is your enthalpy level diagram associated with them. Does that make sense to everyone? Hopefully it does. I know it does because you guys are the absolute best, absolutely smashing it. Oh, hang on. Let me have a look here. So, Michael, you've said that Man United is the best team ever, but you find this lesson is even better. That's fantastic. I think that's the first time I've ever heard that compliment. I think I should get that framed. I might screenshot and just get that framed. Just put it on my desk. I think that's brilliant. I'm glad that that's made sense to all of you. I'm glad that you've enjoyed it so far. So that really sums up the content for today in terms of exothermic and endothermic processes. Now, I guess this is where I'm going to talk a little bit about the importance of exam technique. Since all of this knowledge I want you to all tailor towards your exams, always make sure to remember your signs. So if it's an endothermic process, make sure to put a plus there. And if it's an exothermic process, make sure to put a minus there, because if you don't, you can lose marks because you've not specified whether it's endothermic or exothermic. Okay? With your calculations, also make sure that you leave any rounding to the very end and round to the number of decimal places or significant figures that they have specified. Okay, this goes for all calculations, but always just double check your working out and just set your working out as you go along. Okay, but otherwise, absolutely fantastic. That is it for today's chemistry squad on endothermic and exothermic. Oh, hang on, we've got a question. Where do you put a minus or a plus? So, I'll show you. If you did a calculation and in the calculation you found out that your enthalpy change was 364 kilojoules per mole, if it was endothermic, you need to put plus 364 kilojoules per mole. And if it was exothermic, you need to put minus 364 kilojoules per mole. So this is relevant to your calculations that you do. Okay, if you're asked to calculate the enthalpy change of a reaction, you need to make sure that you state it very clearly, because if you don't, you can lose that mark. Masterpiece, you have asked, what are moles again? Moles are the unit of substance, okay? So moles can relate to how much you have of a particular type of particle or ion or atom. We did have a chemistry squad session on moles, not last week, but the week before, so do check that out. And me, Sam, the positive one is endothermic, the negative one is exothermic. Mikhail, it is a shame that it can't continue forever, but there will be another one next week at the same time. And let me actually check my schedule. I think next week we are going to be looking at... Give me one moment. What are we looking at next week? Next week we're looking at rates of reaction. So we're going to look at rates of reaction next week. So that's going to be a really interesting topic to look at. So do check in for that. That would be great. So it'd be great to see all of you there. Before you leave the session today, Inga has kindly put a link to the feedback form. Please fill out the form because it gives us feedback at my tutor. It helps us know what you guys need. It lets us know what you guys like, and it lets us know what we need to put together to support you guys in being the best students that you can be. So do make sure that you check out that feedback form. Like the video if you enjoyed it. Thank you, Michael. Yeah, do like the video. Smash that like button. I didn't think I'd ever say that. Smash that like button if you did enjoy the video. Also make sure to hit the subscribe button also, and also click on the little notification bell on the My Tutor channel if you want to be notified any single time that the My Tutor channel uploads any content all of which is exciting and tailored towards supporting you in achieving your aspirational grades and beyond. But yes, I will see all of you next week at the same time. I'm glad you all enjoyed the lesson. Um, and there'll be plenty more of these every Wednesday at 5 p.m. So, honestly, like I said before, there is no squad without you all. You guys are absolutely brilliant. And I'm thankful to every single one of you for tuning in because it means so, so much. Um, but yes, I will see you all next Wednesday at the same time. Make sure to smash that like button, hit the subscribe button on the Mighty channel, and I will see you all next Wednesday at the same time. Okay, but take care until then, guys. Take it easy. Have a lovely evening, and keep being absolute chemistry kings and queens that all of you are. I know you're going to smash all of your exams, and I'm proud for all the work that you do. And I will see you all next week. Take care until then, guys.